There is a cooling system hiding inside the walls of buildings that have stood for over 4,000 years. It requires no electricity, no refrigerant, no compressor, and no moving parts of any kind. It can drop the interior temperature of a structure by up to 20 degrees Fahrenheit on the hottest day of the year. Not theoretically, documented, measured, verified by modern thermal engineers who then quietly publish their findings and watch the construction industry ignore every single word. It is a technology that weaponizes the wind itself, that turns the geometry of a building into a mechanical lung that filters, cools, and circulates air with nothing but physics and geometry. And the reason you have never heard of it has nothing to do with whether it works. It has everything to do with who profits when it doesn't. So what is it? How does it work? And why has the billion-dollar HVAC industry spent decades making sure you never think to build one? Let's get into it. You cannot understand why this technology matters until you understand the environment it was built to survive. The story begins in the Nile Delta, in the baked limestone flatlands of ancient Egypt, and across the wind-scoured plains of the medieval Islamic world, where engineers faced a problem that modern architects have simply decided to solve with a monthly electricity bill. How do you keep a building at a livable temperature when the outside air is pushing 115 degrees Fahrenheit and there is no grid to plug into? The answer they arrived at was the Malkaf, also known as the Windcatcher. It was a vertical tower, open at the top, and oriented precisely into the prevailing wind, designed to intercept the fast-moving upper air above the roofline and drive it down into the building below. The earliest confirmed examples appear in Egyptian tomb paintings dated to roughly 1300 BCE. By the medieval period, structures across Egypt, Iran, Pakistan, and the Arabian Peninsula were built with wind catchers as a fundamental architectural organ, the same way we think about a roof or a foundation today. These were not decorative. They were the cooling and ventilation system. They were the building's lungs. But the Malkaf was not just a hole in the wall pointed at the wind. The engineering was precise and it was sophisticated. The towers were calibrated to the regional prevailing wind direction, often oriented within just a few degrees of the dominant airflow to maximize capture velocity. The interior shaft was divided by partitions that separated the inflow side from the outflow side, creating a controlled pressure differential inside the building. In the most advanced iterations, the bottom of the shaft was positioned directly above a sabile, a water basin, or a wet earthenware pot arrangement. As the hot captured air was driven downward through the tower, it passed across the evaporating water surface and dropped in temperature before it ever reached the occupied space. This is evaporative cooling without a single manufactured component. The physics are identical to the refrigerative cycle your air conditioner uses. The only difference is that one of them requires a power plant and one of them requires a clay pot. The performance data on these structures, collected by researchers who have bothered to study them, is not marginal. It is extraordinary. A 2010 study published in the journal Energy and Buildings analyzed a traditional wind catcher in Yazd, Iran, one of the hottest inhabited cities on Earth, and found that the system maintained indoor air temperatures between 14 and 22 degrees Celsius, while outside temperatures exceeded 40 degrees Celsius. In Fahrenheit, that is a building sitting at 64 to 71 degrees, while the exterior bakes at over 104 degrees, without a single watt of electricity being consumed. A separate analysis conducted by researchers at Cardiff University examined the fluid dynamics of a traditional four-sided Malkaf and found that at an external wind speed of just 3 meters per second, a modest breeze, the system generated enough positive pressure to drive a complete air change through the interior space every 7 minutes. That is more than 8 complete fresh air changes per hour. The EPA considers anything above 0.35 air changes per hour adequate for healthy indoor air quality. These towers were delivering more than 20 times that benchmark, using nothing but the energy of the wind. To understand why this is more powerful than a mechanical system, you have to understand what a mechanical system actually does. A central air conditioning unit does not create cool air. It moves thermal energy. It takes the heat from inside your home and expels it outside using a compressor, a refrigerant loop, and a significant amount of electricity to do it. The coefficient of performance for a standard residential AC unit sits between 2.5 and 4.0. That means for every unit of electrical energy you put in, you move 2.5 to 4 units of thermal energy. It sounds efficient until you realize that the electricity itself was generated at roughly 33% thermal efficiency at the power plant, then lost another 6% in transmission before it reached your panel. The actual thermodynamic efficiency of the complete system, from fuel burned at the plant to heat removed from your room, is closer to 1.0. You are moving 1 unit of heat for every unit of heat burned to move it. A Windcatcher does not operate on thermodynamics of efficiency. It operates on thermodynamics of source. The energy source is the wind. The wind is a surplus resource. It costs nothing, it produces no carbon, and it does not send a bill. The Malkoff has a coefficient of performance that is mathematically infinite because the denominator, the energy consumed, is zero. So why aren't these systems on every building in the American Southwest, in Phoenix, in Las Vegas, in Albuquerque, in every city where the grid buckles every summer under the weight of 10 million air conditioners all running simultaneously? The answer is the same answer it always is when a superior technology gets sidelined. It doesn't generate a revenue stream. A Windcatcher is not a product. You cannot manufacture it, box it, ship it, service it, and charge a maintenance contract on it. It is an architectural feature. Once it is built, it is built. There is no filter to replace, no refrigerant to recharge, no circuit board to fail, and no technician to dispatch. The HVAC industry in the United States generates approximately $151 billion in annual revenue. That industry's business model is not contingent on your house staying cool. It is contingent on you being unable to keep your house cool without their equipment. Then there is the code problem. The International Residential Code, which governs residential construction across most of the United States, is written around mechanical ventilation standards established by ASHRAE 62.2. Those standards are written in terms of mechanical fan rates, cubic feet per minute outputs, and rated equipment performance. A Windcatcher has none of those ratings. It is not a listed product. It has no Energy Star certification. It has no UL number. And because a local building inspector cannot point to a line in a code book that tells him what a Malkoff is, he will reject it, require a mechanical backup, and effectively force the homeowner to install the exact system the Windcatcher was designed to replace. It is not a conspiracy in the dramatic sense of that word. It is a bureaucratic immune system that has learned to reject anything that doesn't generate downstream revenue. There is also the matter of orientation. The Malkoff is not a universal technology in its classical form. It requires a consistent prevailing wind direction, and it requires that the building be oriented to capture it. In a tract housing development where every lot faces the same direction regardless of the solar or wind geometry of the site, this kind of intentional siting is not part of the conversation. Modern residential development is optimized for lot yield, not for thermodynamic performance. The site plan is drawn before anyone asks which way the wind blows, but the technology has not been abandoned by the engineers who understand it. It has been quietly evolved. Modern hybrid Windcatcher systems, studied extensively by research teams at the University of Nottingham and at the Politecnico di Milano, combine the classical Malkoff geometry with passive thermal mass, earth tubes, and computational fluid dynamics modeling to optimize the tower geometry for specific wind profiles. A 2019 study in Renewable and Sustainable Energy Reviews documented a hybrid Windcatcher system integrated into a commercial building in the Persian Gulf that reduced cooling energy demand by 62% compared to a conventional air-conditioned building of equivalent size. 62% in one of the hottest commercial real estate markets on the planet. If you want to integrate this into your own construction, here is what the modern implementation looks like. For new construction in a climate with a consistent prevailing wind, the goal is to design the tower orientation during site planning before the foundation is poured. The tower height should be a minimum of 1.5 times the height of any obstruction within a 10-meter radius to ensure clean laminar flow into the intake. The shaft cross-section should be sized at roughly 1 square foot of opening for every 200 square feet of conditioned floor space. The interior should be lined with high thermal mass material, stone or rammed earth to buffer the temperature swings between day and night. For climates with hot, dry summers, the addition of a wetted evaporative pad at the base of the shaft, a modern version of the Sabile, can drop the supply air temperature by an additional 10 to 15 degrees Fahrenheit before it enters the living space. For an existing home, the retrofit path is more limited but not impossible. A wall-mounted passive ventilation tower, essentially a scaled-down Malkoff geometry using an insulated duct and a wind directional cowl on the roof, can be constructed for under $400 in materials and will provide measurable improvements in air change rate rate and indoor temperature stability on windy days. It will not replace a full system, but in climates where the prevailing wind is consistent and strong, it will reduce the runtime hours of your mechanical system significantly. The maintenance profile is what seals the argument. A Windcatcher requires an annual inspection of the intake screen to prevent debris accumulation and a check of the interior shaft for moisture or biological growth. That is it. There are no annual service contracts, no refrigerant certifications, no electronic control boards to replace after a power surge. The system has a functional lifespan measured in centuries, not in the 15-year depreciation schedule of a mechanical unit. We have spent 70 years building homes that are thermally helpless, thin-walled, low-mass boxes wrapped in plastic vapor barriers that trap moisture and toxins, then bolted to the grid by a mechanical system designed to degrade and be replaced on a schedule that benefits everyone except the person living in the house. The Malkoff was not primitive technology, it was sophisticated engineering developed by people who understood thermodynamics before they had a word for it, who understood pressure differentials before calculus existed to describe them, and who built structures that kept human beings alive in climates that should have been uninhabitable. We did not improve on that knowledge when we replaced it with the compressor. We traded competence for convenience and called it progress. The wind was always free. The knowledge of how to use it is what keeps getting buried. If the kind of information this channel covers matters to you, the kind that challenges what we've been told is modern and optimal, then subscribing and sharing is how it keeps reaching people who are ready to hear it. We covered the Malkoff here, a system that uses the wind to cool and ventilate. If you want to see what happens when you apply that same ancient understanding of airflow and pressure to an underground system that keeps buildings cool using nothing but the earth itself, then watch our next video on earth tubes, the 0-watt cooling pipe that has been used since the Roman Empire and that your HVAC contractor has never once mentioned to you.